Today's lecture is on isotopes. This covers the third part of the chapter 17 in our textbook. We're going to be talking about models, reviewing models for atoms. Then we're going to be reviewing atomic mass. There's lots of ways we measure atomic mass. We're going to discuss a couple of them. We're going to review atomic mass units, and then we're going to get on to isotopes, which is today's main focus. Early models of the atom include the Bohr model. There are lots of other ones. This is the one that's still often used because it shows some useful elements. The electrons tells you the number of electrons, number of neutrons, number of protons. It's visual, but it is very misleading. You have the impression with the Bohr model that electrons move in definite orbits around the nucleus, but that's simply not true. So whenever you see this, you have to realize this is just a representation. It is not how it really acts in real life. This is closer to what acts in real life. This is the modern model of the atom. It's the electron cloud. It's sometimes called the wave model, though most times I've heard it referred to as electron cloud. Each dot shows the probability of the electron being placed there. In other words, if you took a still picture, where would that electron be? When you put a lot of dots together, it forms a cloud. So the cloud shows where an electron is more or less likely to be. Darker areas, more likely to have an electron there. Lighter areas, you are not as likely to find an electron there if you took a picture. Atomic mass, it's not its direct mass. We have no way to determine a direct mass. We can only compare it to a known entity, in this case AMU, the carbon atom. Here we have a picture of helium symbol. Above it is the atomic number or proton number, often referred to as Z. So the atomic number is the number of protons. Remember, all elements are classified according to the number of protons. You have the symbol He that everybody agrees to use, and then you have the atomic mass in AMUs. That's compared to 1/12 a carbon atom. The atomic mass of an atom is only one atom at a time. This is one thing you need to be clear of. When you're talking about atomic mass, you're not saying what's the average. You're saying take this one atom, what is its specific information? And again, it's defined in AMUs. AMU, for review, is 1/12 the mass of a carbon atom containing 6 protons and 6 neutrons. Again, when we refer to mass number or any kind of number, it is mean count. So there's the Count from Sesame Street, if you don't remember that popular figure. I always liked them. Mass number is not to be confused with atomic mass, not to be confused with the average atomic mass. It is a count. You take the count. How many protons was he able to count? How many neutrons was he able to count? One other thing I wanted you to notice about this diagram. So it's showing carbon, and it's classified as carbon because it has only 6 protons, but it has extra neutrons, and we're going to get into that. That's what an isotope is. Notice how it shows it here, though. It shows carbon, and then to the right, it shows the atomic number, mass number. This is not a common way to write that, more commonly on the left, as we're going to see, but I want you to realize there are other ways to show the same information. So here's today's main point. Isotopes. What is an isotope? An isotope is an atom of the same element, that means the same number of protons, with different number of neutrons. That's the definition of an isotope. It doesn't have anything to do with electrons. It is neutrons. You have the same element, so the proton stays the same. It's the neutrons that are varying. Here's an example of 3 isotopes of hydrogen. You have the most common form, that first one just has 1 proton, doesn't have a neutron. The second version has 1 proton and 1 neutron. And then the third isotope, most common isotope of hydrogen, has 2 neutrons and only 1 proton. Of course, it's only 1 proton. I don't have to say how many protons, otherwise it wouldn't be hydrogen. What about the mass? We've talked about we'll use hydrogen as an example. You have 1 proton. What does adding a neutron have to do with the mass? If you'll recall from a previous lecture, the mass of an atom is in the proton and the neutron. They're equally massive. They're 2,000 times the size of an electron. So if you have hydrogen and you add one neutron, you just doubled its mass. It is twice as heavy as it was before. And heavy, we probably shouldn't use heavy because heavy refers to the force of gravity. However, that is commonly used, but it really would be more correct to say mass, twice as massive. So more about isotopes. The number of protons for a given atom never changes. So if you change the number of protons, you've just changed your element. The number of neutrons can change. Not often, but it can. That's what we call the isotope. Two atoms with a different number of neutrons, the same number of protons, are called isotopes. Isotopes have the same atomic number because what is number again? Atomic number is the number of protons. Isotopes, however, have different atomic mass numbers. Remember, atomic number is what? Number of protons. Mass number is what? Mass number is the number of protons plus neutrons, because that's what the mass is. The mass of parts, not the electron, it's the protons and the neutrons. How do we write them? We write them in the form of standard notation, or it's often called AZE notation. You have the A stands for mass number. You can see in this diagram that's protons plus neutrons, and look, it's got the charge there. You have a positive charge for protons and a neutral charge for neutrons. The atomic number below is the Z. I've always wondered about this form. Why are you showing the atomic number when you have the atomic symbol? Isn't that a duplicate? We'll have to ask some scientists someday. Here's an example of helium. You see the element symbol there to the right, and then it shows two numbers, one over the other. The top number is the mass number. It's always going to be larger or the same as the atomic number, never less, because it includes the atomic number. Here's an example with hydrogen. Again, this is the same thing we saw before, but this is using the standard notation. The first one, hydrogen, is showing the 1 over the 1, and then it's showing the second one with 2 over the 1, because you have an extra neutron. And then the third isotope shows 3 over 1. So you start with the 1, you have 1 proton, and then remember that top number 3 is the number of protons plus neutrons. So how many neutrons do you have for trillium? 2. Naming isotopes. When we name some of these isotopes, we often don't put the symbol. We write it like boron 10, boron 11. It's just prettier that way. It's like writing it out using correct English all the time. So when you need to name it, you might say boron -10 -11. What do you think that 10 is? Yes, that's the mass number. That's the number of protons plus the number of neutrons. Uranium, often written uranium 238, telling you what the mass number of. And just in case you're wondering, it breaks down to lead. This is one of those few reactions that occurs at the nucleus level into lead. Of course, it takes a bit of a time. It takes about 4 billion years, but it does eventually happen. And then we have carbon-14, which breaks down a lot quicker into nitrogen. The reason I'm mentioning it here, it's often used for carbon dating. They use carbon-14 because it naturally breaks down into nitrogen. It takes about 6,000 years, though. And last, this is a slide showing you helium. Before we showed it as helium-5, here you can see it as 5-helium. Again, I want you to be comfortable with the various ways scientists use for showing this. The 5, what do you think that 5 means? Looking at the atom, you can see two different colors. Unless you have two colors, you have 2 of the red and 3 of the yellow. And let's go to 6 helium. You still have 2 red. That stayed the same. What's that tell you? Yes, there's 2 protons, because otherwise it would be a different element. So the red we can think of as the protons, which makes sense. Helium has, if you look at a periodic table, which you should be by now, helium has 2 protons. So we see 2 protons, 3 neutrons equals 5 atomic mass. I hope you enjoyed this. I hope you learned something from it. And please review the textbook for additional information. Enjoy.